column buckling is one of the important criteria I discuss with you. Let me share with you why it happens. So we should know how it buckles, and then you should know why it buckles. So as a structural engineer, what you should do. So let me quickly discuss with you. For example, you can understand here why there is a buckling. Say we have one column like this, okay, and due to the compression, this buckles. So do you know why it buckles? What is the reason? कोई बता सकता है? Why there is a buckling of this column?
सर स्लेंडरनेस रेशियो अगर ज्यादा होगा तो बकल हो जाता
Yes. So yes, we can say, and this is, let's say, let me take one more example. Say there is a column and there is a compression here, and the column size is same for both the cases. First case ये और ये दोनों में सेम है. ये केस 1 है, केस 2 है. टेल मी हु विल बकल फर्स्ट. ये पहले वाला बकल होगा या दूसरे वाला? हु विल बकल फर्स्ट?
फर्स्ट वन.
First one.
Yes. So this deflection or buckling deflection, we can say horizontal deflection, is more in first case and less in this. So this is more buckling and this is less buckling. Can you tell me what is the reason? Because this length is more. So whenever there is a more length, buckling is more, and if the length is less, buckling is less. Okay, so this is one criteria. So whenever you design any structures, make sure that your slenderness ratio, actually slenderness ratio is L effective upon R minimum. So if length is more, you can see slenderness is more and buckling is more. Try to understand this. Now let me take one more example. Say we are having the same column height. Column height is same, but the cross sectional size of the column is more. जैसे बड़ा column है एक, say ये 200 by 200 का है समझो column, and say this is 400 by 400. Okay, height or length is same, both length are same, L1 let's say and L1 also. Now tell me who will buckle first?
200 by 200.
So this will buckle
Buckle
first and
first.
it will buckle more also. Okay, so let's say this is your buckling lateral, and in this case there is, we can say, less buckling. Now what is the reason? Length तो same है तो buckle कम क्यों? Right. What is the reason? This delta is less and this delta is more, even though height is same.
Width is less.
Yeah, so we can say the cross sectional area is more here and is less here. Right. So cross sectional area, if it is more, and that too in the buckling direction, this depth is more. Try to understand, it is buckling in this direction, so this should be more, depth in this direction should be more in the buckling direction. So there is one term which is related with the cross sectional area A. There is one area A also, and this depth is more, that means the moment of inertia I is also more. Try to understand this. So we can say deflection is something related with the moment of inertia, Mi or I, we can say. It is something related with the cross sectional area also. Now there is one term in the structural engineering that is called as the radius of gyration. Okay, R, which is nothing but root I upon A. So try to understand, if the moment of inertia, this R is more also, we get less deflections. So what is the solution to increase the capacity of the column or to reduce the buckling? What can we do? If you want to reduce the buckling, what can you do?
You should increase cross section area or width.
Yes, so you increase the cross sectional area or that depth along that buckling direction. That is one criteria. Or you reduce the height of the column, or length of the column, whatever you say. Say I can provide one beam here. If I provide one beam here, say, then definitely now the height is less. So this is L by 2 now. This is L by 2. Now this will not buckle like this, but it will buckle something. Let me show you the single line diagram only. So it will buckle, say like this. So this delta is now less because this L is less. This is something related with the slenderness ratio. Or you can increase this cross-sectional area and depth in this direction. So increase this depth. So these are the bucklings in the structures, and if your design is not having sufficient this depth, okay, many times you don't have a control on the height of the column, then only choice is to increase this depth. Okay, depth, once you increase the depth, the moment of inertia will increase, right? D is more, then moment of inertia is more. So all of you know that the formula for moment of inertia is for rectangular section BD cube upon
D cube
12.
by
So
12.
if you increase the D, it will increase by cubical proportion, right? D cube. So if you have this D, if your D is 200, it is 200 cube, and if it is having 400, then 400 cube. So I will be enormously increase. Okay. So the choice of controlling the buckling is to increase the moment of inertia, means increasing the depth of the column in this direction, in the direction of the buckling, probable buckling we can say. Then there are some terms like web buckling. So if there is a more load, you know that this web of the beam buckles. The philosophy is same like columns. You know, if you draw this I section like this, many times if you have more depth of the web, and if there is a load on this beam, then this buckle, this whatever wave you call, there is axial compression in this wave and it will buckle like this. Okay, or it will either buckle like this or it will buckle like this. I can show you something like this. There are different possibilities. It will compress down and it will buckle like this. This is delta. What is the reason? Reason of this wave buckling, same column, whatever philosophy you are saying, the slenderness ratio is more in this, lambda L effective upon R minimum. Either this depth is very high, the D is more, or this thickness is less. Any reason it may buckle. What can you do in this case to control the deflection, to control the buckling? Increase this, increase the width of the this thickness of the web, increase. So this is the choice. There are certain other methods also by which you can control the web buckling. You can provide the stiffeners here. There is a stiffener plate you can provide so that the span of the buckling will be less. By this also you can control the buckling. See, the terms are very important. Buckling is something related with the compression. Even here also you can see, now we have already discussed this philosophy. Due to the load, as this pipe thickness is less or slenderness is more, it is buckling. Many times you can see the clear cut deflected shape in the steel structures, but in RCC structures you cannot see the clear cut deflection like this, the way we draw on the paper. But by looking at the cracked pattern, and there is a bulging of the steel out of this column, so you can understand that there is a more compression and there is a buckling. So in RCC we cannot get the exact behavior because of the properties of the concrete, aggregate, cement and all, but in steel structure it will give you clear cut deflection or buckling. So these are the theoretical pictures we can say. If this is the length, this is the deflection. If there is one additional support here, the deflection is less. See this. So because this is L by 2, L upon 2, let's say this is your total L, L by 2 less, and if it is L by 3, again very less, very less. So you can add the supports, or rather you can reduce the length of the column and you can control the buckling. Yes, now these are also same things. This is buckling. So buckling is something we can say it is a lateral load due to compression. That is buckling. There is a bulging of the column also, bulging. Cross-sectional area will bulge like this. See this. So this is not buckling, but we can say this is bulging. This is a kind of deflection only, but because of when it happens, because the cross-sectional area is very less and there is more stress in the column, and this will bulge. And there is a shear failure also like this. If there is no sufficient shear capacity, then this will slide. This is also kind of deflection. We can say it is a shear deflection, okay, or shear deformation. So there are many different words used in the structural engineering. Every word has a meaning, okay. Bulging, buckling, and shear deformations. Once you look at the structure, you should be able to understand what is the reason and what is happening there inside.